So building on what we learned in the acid and base unit, we'll move on to Unit 5 here and discuss pH and pOH. pH we discussed in the last unit, but we have not yet discussed pOH. To lead us into this, I'll say that the pH is a measure of acidity, something you've maybe had other experience beyond what we did in the last unit. And pOH, maybe that's not something you've had experience with, but we can see that in the pH there's hydrogen represented, and so that leads us to say it's some sort of measure of hydrogen concentration, and the pOH a measure of hydroxide concentration, which also plays a role in our discussion of acids and bases. So, what's wrong with this picture? In fact, there are quite a few things wrong with this picture, but we can see that the gentleman here is sitting in the tub, potentially filled with water, and using a hair dryer that is plugged in. You can see the cable running out of the tub there. And it's something that, of course, we know that is dangerous. However, the question might be, well, why is that dangerous? And so part of what we'll explore here at the beginning in order to introduce the concept of pH and pOH is a little bit about, well, why exactly is electricity mixing with water a dangerous event? So to understand the concept of pH and pOH, we first need to discuss the concept of the ionization of water. Water conducts electricity. This is something that we've been told in terms of safety, and we discussed that in the picture that we just saw, but how does water conduct electricity? Here's the concept that we really need to understand. Water molecules don't stick together all of the time. And so we have the H2O that is shown in the water to the right here. But really that H2O, as we'll see in a moment, is made up of hydrogen ions and hydroxide ions. Sometimes when those water molecules run into each other, they bounce off each other and they break apart into the hydrogen and the hydroxide ions. And it's the positively charged hydrogen ions and the negatively charged hydroxide ions that result in allowing water to conduct electricity. So, as we just said, when water molecules break apart, what ions are made? Hydrogen ions and hydroxide ions. Before we look at the chemical reaction here, we can see that, well, we have one hydrogen ion and a hydroxide ion combined. There are two hydrogens, H2, and one oxygen, O. So H2O in the chemical reaction is written as H2O, liquid, will break down into hydrogen ions dissolved in the liquid, so aqueous, and hydroxide ions, again, dissolved in the water, aqueous. Overall, the glass of water that we showed in the slide earlier is mostly water molecules, but there is some hydrogen and some hydroxide ions dissolved in the water. In pure water, the concentration of hydrogen ions is exactly the same as the concentration of hydroxide ions. For every one hydrogen ion, there is one hydroxide ion. This is an important concept to think about, and I want to relate it back to what we learned about for acids and bases. We learned about water being neutral, and that acids give off hydrogen ions and bases give off hydroxide ions. For every one hydrogen ion in water, there's one hydroxide ion, so there's an equal amount of acid and base. Therefore, water is neutral. There's an equal amount of acid and base within the water. So the pH of water is 7, neutral. It's neither acidic nor basic because it has equal amounts of acid and base. Square brackets, shown here, show the concentration of something. So we will start to use those throughout this unit. The concentration of each ion is written then as follows. The concentration of hydrogen is 1.0 times 10 to the negative 7. This is a value that is given for water. The concentration of the hydroxide ion in water, in this case, is 1.0 times 10 to the negative 7. So again, we can see the concentration of very small. These are very small numbers, but we can see that there are equal amounts of hydrogen ions and hydroxide ions. Great. So what? What does this all mean? Another property of pure water is called the ionization constant, Kw. Kw has a value of 1.0 times 10 to the negative 14. Where does this number come from? It comes from multiplying the concentration of the hydrogen ions times the concentration of the hydroxide ions in pure water. The values we looked at in the last slide, 1.0 times 10 to the negative 7 times 1.0 times 10 to the negative 7 equals the 1.0 times 10 to the negative 14. The point in the end is we can use this information to find hydrogen ions or hydroxide ions of any aqueous solution, specifically any acids and bases that we would be interested in investigating. For example, an aqueous solution has a hydroxide ion concentration of 7.5 times 10 to the negative 4. What is the molar concentration of hydrogen ions in this case? In order to do this, we need to do a few steps. The first is write down the formula. Hydrogen concentration times the hydroxide ion concentration is equal to 1.0 times 10 to the negative 14, as shown here. The second step is rearrange to isolate what you're trying to find. In this case, the question is asking us the concentration of the hydrogen ions. We want to rearrange the equation shown here in order to calculate and isolate the hydrogen ion concentration. How we do that is we want to divide both sides by the hydroxide ion concentration. That gives us this form of the equation. The hydrogen ion concentration is equal to 1.0 times 10 to the negative 14 divided by the hydroxide ion concentration. In the end, we can then sub in the given. The hydroxide ion concentration is the 7.5 times 10 to the negative 4 as given in the equation. And then we can calculate out, finally, the answer. In our calculator, we'll come up 1.333 times 10 to the negative 11. Of course, we want to keep track of significant digits in this case, and so the answer should be the hydrogen ion concentration is 1.3 times 10 to the negative 11. Why don't you try practicing this question? An aqueous solution has a hydroxide ion concentration of 2.1 times 10 to the negative 10. What is the molar concentration of hydrogen ions? I'd suggest pausing the video at this point and trying this question on your own. Okay, so in the end, the logic is the same as the sample question we went through. We write out the equation. We want to rearrange the equation, in this case, solving for the hydrogen ion concentration. So we divide by the hydroxide ion concentration. There's our rearranged equation, and again, we want to then plug in the 2.1 times 10 to the negative 10, and we get an answer with two significant digits, 4.8 times 10 to the negative 5. Another type of question that we might come across is one like this. If an aqueous solution of HCl is 0.2 molar, what is its hydroxide ion concentration? The first thing we need to do is ask ourselves, is HCl an acid or a base? Since the HCl has hydrogen within it and no oxygen, there's no hydroxide ions here, we can see that if it were to dissolve in water, it would give off the hydrogen as hydrogen ions, therefore defining it as an acid. So what is its hydroxide ion concentration then? Well, the 0.2 molar represents the hydrogen ion concentration because we're dealing with an acid. And so we can write out the same equation that we've been looking at, but in this case, we're going to rearrange the equation by dividing both sides by the hydrogen ion concentration. Thus, we end up with the hydroxide ion concentration is going to equal 1.0 times 10 to the negative 14 divided by the hydrogen ion concentration, and we can plug in the 0.2. That gives us an answer of 5.0 times 10 to the negative 14. Now that we've calculated the hydrogen ion and hydroxide ion concentration, we can move on to calculating pH. Recall the pH scale. We've looked at it previously in the last unit, and now we're starting to calculate the hydrogen ion concentration. The connection here is that we can convert between the pH scale and the hydrogen ion concentration. Because there's a relationship, the pH scale is a little bit simpler to use, 0 through 14, as opposed to the hydrogen ion concentration with the scientific notation and so on. We can convert from pH to hydrogen ions and from hydrogen ion concentration to pH. So this is where we've come. pH is a measure of hydrogen ion concentration. It's based on a logarithmic scale. Moving from a pH of 8 to a pH of 11 is 3 steps up the pH scale, but it's equivalent to multiplying 10 by 10 by 10. A pH of 11 is 1,000 times stronger than pH 8. So for example, going from pH 8 to pH 9, in pH 8, the hydrogen ion concentration is 10 to the negative 8. The pH 9, the hydrogen ion concentration is 10 to the negative 9. That's a jump of times 10. And that continues. pH 10, hydrogen ion concentration, 10 to the negative 10. And pH 11, and so on and so forth. Each step in a logarithmic scale is multiplying times 10. So it is 10 times more acidic or 10 times more basic, depending on the way you're moving on the pH scale. To find pH, we have an equation that we need to remember. pH is equal to the negative log of the hydrogen ion concentration. Or, if we wanted to do the inverse and find the hydrogen ion concentration, it is equal to 10 to the exponent, the negative value of whatever pH you have been given. We need to memorize these. You're not given these equations come the test time and exam and so on. And one thing that students often forget are these negatives out in front of the values. Okay, another thing we need to remember, and as I have in the title here, it's kind of an annoying pH Sig Dig rule because it differs from all the other Sig Digs that we have looked at previously. When working with pH, Sig Digs start getting counted after the decimal. This is going back to the logarithmic scale. It throws a little twist into things, and so let's look at a couple examples. If I have a pH of 4.2, 5.6 or 11.5. All of these have one significant digit. According to our previous rules, we would have not said 1 for significant digits, but when dealing with pH specifically and pOH, we have one significant digit because we only count whatever's after the decimal place. All of these values shown here have two significant digits. Each of these values we also treat as one significant digit. So again, as I said in the title, an annoying pH Sig Dig rule, but it's something that we have to get used to and practice as we go. So let's look at some example calculations. Calculate the pH of the following solutions given the molar hydrogen ion concentration. Let's look at vinegar first. Vinegar has a hydrogen ion concentration of 0.001 molar. So to calculate the pH, we take the negative log of the hydrogen ion concentration. You can plug it into your calculator as shown here, negative log of 0.001. There's only one significant digit in our question. So the answer we should record, 3.0. You might say, hey, but that's two significant digits. But again, this counts as one significant digit because we're only counting in pH the value after the decimal place. And so the 0 here is the only significant digit that we're recording. Let's look at part B here. We have 0.000000012 molar concentration of hydrogen ions. There are two significant digits in this case. And so we plug this value into our calculator according to the equation negative log of the 0.00, etc., etc., and we get an answer of 7.92. It looks like three significant digits, but this counts as two significant digits because we only calculate the values after the decimal place for pH questions. Let's look at another example. Calculate the molar hydrogen ion concentration given the pH of the following solutions. So in this case, we're going from pH to hydrogen ion concentration. If we look at part A here, lemon juice, the pH is 2. How do we plug that into our calculator? There are a number of different ways depending how your calculator works. And so we want to say the pH is 2, and we want to plug that in as a negative exponent for the value 10. Depending on your calculator, it will be 10 and either the XY button, or some people have a little upside down V that represents the to the power of, and then negative 2 in the calculator. This counts as one significant digit, the pH of 2. And so we get 0.01 in the calculator, and we can represent that as 1 times 10 to the negative 2 molar as well for the concentration. This answer has, again, one significant digit. We look at the second question here for tomato juice with pH 5.2. Again, we can plug it into our calculator according to the same process, 10, and then either xy or the upside down little v for some people's calculators to the negative 5.2. There's one significant digit in this pH of 5.2. So we look at our answer in the calculator, we get 6 times 10 to the negative 6 molar, and this again is one significant digit. One thing I'll pause here to reflect on, in the pH, after the decimal is one significant digit. In the molarity, or the concentration of the hydrogen ions, our significant digit rule is the same as always. So in this case, the 6 counts as one significant digit. We do not need to put 6.0 in this case. Now we can start to look at advanced pH calculations. The same calculations that we've looked at so far for pH work for pOH and the OH minus concentrations. So pOH is the negative log of the hydroxide ion concentrations. The hydroxide ion concentration is 10 to the negative exponent of the pOH. So we can look at the following questions. Calculate the following. pOH when the hydroxide concentration is equal to 0.00012. We plug it into the same way we did in our calculator for pH, negative log, but this time of the OH minus ion concentration. The answer we get is 4.92. Again, I'll point out that the 2 after the decimal place in the hydroxide ion concentration is 2 significant digits. In the pOH, we again have 2 significant digits, but we have this weird rule after the decimal place. The 9-2 are the significant digits. Calculate the hydroxide concentration when the pOH is 8.3. We plug that into our calculator. 10, use the xy, or again the upside down v, to the negative 8.3. And we get 5 times 10 to the negative 9 molar. In the pOH, 8.3, we only have one significant digit for the 0.3. And so in the molarity, we have 5, which represents one significant digit. In the end, a bit of a formula summary. Kw is equal to the hydroxide ion concentration times the hydrogen ion concentration, which equals 1.0 times 10 to the negative 14. We need to remember that. The ion concentration represented by the values that we just finished looking at. The pH and the pOH equal to the negative log of the respective ions. Additionally, we need to recall that the pH plus the pOH will always equal 14, because the pH represents the number of hydrogen ions and the pOH represents the number of hydroxide ions, and in total they will sum to 14. We need to watch significant digits, those are tricky, and also remember the signs. In addition to this slide, I've also provided a formula cheat sheet so that you can use it during practice that relates pH to pOH, the hydrogen ion concentration to the pH, the hydroxide ion concentration to the pOH, and the hydroxide ion and the hydrogen ion concentration to each other. This cheat sheet can be printed off the pH-pOH module within DC Connect. It can be useful again for practice, because of course practice is key to organize your thoughts around these types of calculations. So in the end, putting it all together, calculate the pH of the following solutions. A solution with pOH of 3.2, a solution with a hydrogen ion concentration of 5.7 times 10 to the negative 2, and a solution with a hydroxide ion concentration of 3.2 times 10 to the negative 12. For part A, we want to find the pH if given the pOH of 3.2. The pH plus the pOH will equal 14. If we rearrange that equation, 14 minus the pOH will give us the pH. We need to keep track of the one significant digit in the 3.2, and so our answer for pH, 10.8, has one significant digit. For the solution where we're given the hydroxide ion concentration, the pH is the negative log of the hydroxide ion concentration. We had two significant digits in the 5.7, and so we need two significant digits for the pH, but in that case it's after the decimal place. For a solution with OH minus concentration of 3.2 times 10 to the negative 12, first we can find the pOH. The pOH is the negative log of the hydroxide ion concentration. And so we want to keep track of the significant digits, but leave the value that we get here in the calculator. In the end, we will need two significant digits when we get to finding the pH. From the equation, the pH plus the pOH will equal 14. We rearrange that question, and we end up with 2.51, two significant digits, the 5 and the 1, for the answer. In the end, this unit is quite a bit of math. And really the cheat sheet and so on, following through the logic is definitely key. Practice is key as well. So go to your practice booklet, try the questions that are found there, and also I would say go to Sal's if you have any questions, because I'm out of town for the week. I can also try to answer questions via email, but Sal's is probably your best resource for this time.